And looks like we are live. Okay. Hello, everybody. Welcome to our live chat. Of course, I'm going to do my typical check to make sure everything's working properly because I am paranoid that I'm going to screw it up. And looks like we're good. Okay. Make sure that's good. Alrighty then. Well, we have a lot to talk about. First, the background here, if you notice any flashing lights, we have for some reason a ton of police officers. Perhaps they just want to get on the show. I don't know. They're just hanging out, but it's very interesting. So we'll see what that's all about as we get through our chat. Always something going on crazy. I have a lot of things that I want to talk about. First of all, the very foggy conditions. I want to cover that. Of course, our ice threat, and I want to talk about how I came about the forecast, and we'll go over the forecast we have out with the public map that was issued already. And also we'll take a look at the new 18Z guidance and some HRR guidance. And I want to talk about how that forecast for ice. And we'll also talk about the February forecast and what I'm seeing there and why I made some slight changes to what I was just thinking 10 days ago to where I am thinking now and why I'm going with where I'm going. And I won't answer the door if they knock. No, they won't knock on my door. We're pretty quiet. But that'd be funny, right? I know actually a couple of police officers with Frio Township where I live, and they're big fans, mostly because I answer their phone calls when they're wondering, hey, am I going to get stuck in this snow and ice? How do I prepare for it? So first of all, let me show you some observations. Of course, premium chat will answer all of the questions there. And then we'll check out YouTube and see what's popping up over there. I see you guys, 52. And also, I want to also say thank you to the subscribers on the YouTube channel. We've broken 2,000 subscribers. And I find that, I mean, look, I know a lot of channels are like 1 million, right? So it's like 2,000 is like nothing to people like that. But to me, it's like, I have no idea what I'm doing. I'm just sitting here talking about the weather and, you know, getting 2,000 subscribers as an independent meteorologist to me is pretty cool. So I just want to thank you guys for subscribing. I really appreciate it. So where should we start? Oh, well, let's start with the observations. Let's zoom in here. Whoop. Okay. And computer went a little wacky. Sorry about that. All right. So we have a lot of fog popping up around here. Now, the reason why is because of our temperatures. How, you may ask? Well, we have a snowpack of anywhere between 6 inches to 2 feet. And you have temperatures that are above freezing with not much in the way of wind. You combine those two factors together, and what you end up with is a perfect scenario for some very dense fog. So I know some of you guys actually work overnight, deliveries, stuff like that. Use extreme caution tonight into tomorrow morning. This fog is going to be, well, I mean, it's already getting close to zero visibility. Parts of Long Island's down to a third of a mile. Parts of New Jersey, Freehold out here, it's like pea soup. You know, it's you can barely see outside. So it's pretty bad. It's down towards southern New Jersey. We're down to a third of a mile. This is typically what happens after you have a very thick snowpack, and then you get your temperatures to warm up, and you get a night like tonight where temperatures are going to stay above freezing the whole night. So you get all that low-level moisture in the air. You don't have much in the way of winds, and that's a perfect setup for locally dense fog to form. Now, the good news is that we're going to stay above freezing. And the reason why that's good news is that sometimes when you have a snowpack in place and temperatures are right around 32 degrees, you can get freezing fog, which is really bad because basically you get this rime all over the place. It's easy to slip on the ground. With temperatures being above freezing, basically in the mid 30s to low 40s, we don't have that problem And although the visibility will be bad, at least it won't be too icy out there. Meanwhile, we have our Arctic cold front. Now, this is a very interesting scenario here. I know that the model guidance is going really crazy with the ice. I have my doubts on some of this output. Okay, now the forecast I have in place right now basically has almost no impact for the Jersey Shore, much of the Jersey Shore, maybe northeastern Monmouth County gets a little bit of ice, but for much of the Jersey Shore, not much of a concern. Then we go a little bit more to the north and west, and we're looking at more like a trace to a tenth, maybe a trace to maybe an inch of snow at the very end of this. And then further north and west over the interior, basically northwest I-95 corridor, this is where these two sections are where I'm really concerned about ice. We're talking about Allentown, Lancaster, Harrisburg, portions of northern New Jersey. And this is where I am going with a tenth to a quarter of an inch ice. Not much in the way of snow in this type of scenario because of the way that this whole setup is happening. You have the Arctic cold front coming through, and you have very cold air coming in at the surface. But the whole process of this cold front, because of the upper level winds, which I'm going to show you, sets up a scenario where you have your low level cold air coming in first, and then the mid level cold air comes in. And as a result, this is how you get that ice threat. Back here is where I'm concerned for up to about a half an inch. Now, this half an inch of ice is going to be more isolated, but I can't ignore the potential. Most locations would be around a quarter. And right in this zone here is where I'm expecting that. And then finally, 2 to 5 inches, a little bit more snow potential. And then your heavy snow much further north up towards Albany. This map that I generated, of course you use model guidance, but a lot of it has to do with more of the threat of the use of climatology and knowing what these scenarios typically produce. And the models typically have a difficult time with this. For example, in New York City, I know that some people were looking at the output for like a quarter of an inch of ice. Now, why am I not going with that? Well, because New York City is an urban heat island, and it has subways, and it has very warm streets, and it has a lot of people. And what does that all equate to? It equates to the fact that you need your temperatures, your air temperatures, to be basically between 25 and 29 degrees to support an ice event. Whereas in this scenario, you're going to be falling into the lower 30s, and by the time the precipitation gets here, it's going to be pretty much done. So let's take a look at what we have here in this scenario here. Okay, I'm going to walk you through how to do an ice forecast. So that way you guys can get a pretty good understanding of how to go about this whole process. So, because, the point here is to educate as well, not just say, oh, this is my forecast and why, but also give you guys a good idea of how to go about these forecasts, and so that you don't get trapped in this, chasing models and whatnot. So in this scenario, first of all, we have strong warm air transport. We have plenty of moisture coming out of the Gulf of Mexico, plenty of deep moisture. Notice the trend here. Your deepest moisture is back here. You have a short wave here creating all sorts of havoc in Oklahoma, producing snowfall. This is associated with an inverted trough back here. You see how the trough goes back here? And this is just a nightmare for Oklahoma. Believe me, I lived out there. When it snows in Oklahoma, basically they wait for it to melt. It's just a mess. So this is equivalent of having 3 feet of snow in New York City and Philadelphia. When you have like an inch or 2 or 3 inches, forget about 4 inches of snow. 4 inches of snow, forget about it. They shut down for a week. It's a disaster over there. So you got this set up here, but notice the bulk of your moisture transport is out here. Again, we have our nice warm air transport. Let me zoom out here and pull up the moisture transport, and we'll go to full sector. And the reason why I'm pointing this out is because you want to understand the nature of the storm. Is this a scenario where we have strong waves of low pressure, or is this a scenario where we have an Arctic cold front with weak waves and the bulk of your moisture transport is out ahead of the cold front? Well, for the most part, it's out ahead of the cold front. Now, what makes this scenario interesting and unique is the fact that you have a positively tilted trough. Why is that important? Because when you have a positively tilted trough in an Arctic cold front, the winds run parallel to the cold front. So what happens is that the cold front moves slowly, and your cold air at the surface is slowly moving east, but the mid-levels are even slower. So you get that moisture transport, and that is how you get the moisture to set up behind the cold front, because it's kind of like a slope, okay, of moisture riding up against the cold dome that's trying to push east. So that is how you end up with this scenario for snow and ice because of the nature of these upper level winds. And you can see that pretty well at 850 millibars. Let's see, zoom in a little bit. There's your winds running parallel to the isotherms. And when you have that, that's called slow cold air transport. Now at the surface, in fact, we'll do near freezing temperatures. Perfect. At the surface, notice the difference. The winds are blowing from north to south at the surface. Why is that important? It's important because you recognize that with this cold front structure, the low-level cold air transport is stronger than the mid-level cold air transport. This allows the whole setup and the potential for ice, okay? That's why we're in this scenario. But you also have to recognize, and the models don't always do a very good job on this until you get a little bit closer into the scenario, that you got all of this topography here. You got the geography of the Appalachian Mountains, valleys. You have, of course, the I-95 urban heat island effect. So with those factors, what you get is more of what we call, or what I call, kind of a drag, a geographical drag or orographical drag. And what that means is that cold air doesn't just uniformly drop down into the coastal plain, but kind of runs through valleys, gets hung up around the mountains, and then slowly creeps down towards the coastal plain, especially in a scenario where you do not have strong mid-level cold air transport to allow for mixing and to push the cold air at the surface even faster. That's far different than what you have here in the Great Lakes, where you don't really have that impediment. So that is a factor to consider in this scenario. So there's your water vapor satellite picture, and there's your little short waves associated with this whole setup. And so let's take a look at some of the model guidance here. Now our NAM model guidance, now remember earlier, especially with the GFS, it was suggesting all of this freezing rain all over the place. Now the GFS has a significant cold bias error. It also has a problem with recognizing all of these small mesoscale factors that we were just talking about. Urban heat island effect, the topography of the northern mid-Atlantic. And so it typically overdoes the ice threat here. Now the NAM, the 18Z NAM, and we'll wait for the 0Z to come out, clearly is much, much warmer. Notice the bulk of our precipitation in the northern mid-Atlantic is coming in the form of rain. And we don't get the cold air transport until later on in the morning, and by then, the bulk of your precipitation is done. You get a little bit of area of snow. There's your trace to 1 inch that you can get down the coastal plain, but that is about it. The HRR guidance, let me just go pull that up. And you want to use the NAM and the HRR guidance at this point because it does a better job handling the mesoscale factors. And we'll use let's see here, simulated radar, and we'll get 0Z. We're going to come back to this because it still hasn't fully come out yet. So we're up to there. Let's pull up the 18Z. This is the last 48-hour one. In the 18Z guidance, notice the progression. Notice the progression being shown here. And the one thing I love about the mesoscale models is that, look at this. You could actually see how the cold air is coming into these valleys. You can see how it's forecasting it properly around the mountains and around some of these valleys, and how it kind of sneaks in, right? The sleet, it doesn't have as great of an impact on the mountain ranges and whatnot, but you can still see some of that influence. Okay, now sleet is because you have a deeper cold air layer. But you can see the mesoscale models do a much better job of handling those factors. Whereas the GFS typically is kind of like a straight line. Even the European is typically more of a straight line. So you could see that by the time the cold air gets down towards the coastal plain, the bulk of the precipitation is nearly done. And again, we're starting at a point where we have temperatures in the 40s and 50s, so you still have to take time to cool down the boundary layer, even if your air temperatures are falling down to around freezing. And we'll come back to 0Z as it loads in a bit. We'll come back to that and see what the 0Z is doing, and then we'll check out the NAM guidance. And again, I'm going to be answering all your questions in just a few minutes. I just kind of want to walk through the thinking of this forecast. Now, here is the latest European guidance. This is the 18Z guidance. And again, the 18Z, the one thing I love about the European guidance is that, especially the more, I guess you call it HD version, okay, the more concentrated version, or the elevated version in terms of the resolution, is that much like the NAM guidance and the HRR guidance, it does a better job of picking up the valleys and how the cold air is trying to bleed down into those valleys, and where the cold air is kind of getting held up by the mountain ranges that we have in place here. So notice we have rain for the most part, and the thing with this rainfall, again, with the melting snowpack already and the ground being saturated, there will be that potential for some urban flooding. I'm not too concerned about river flooding based on where we are at, but definitely some urban flooding is going to be an issue here. Notice the cold air takes its time to get south, and by the time it does actually gets its job done, it's already done, most of the precipitation. So you don't want to go heavy in this scenario. And I stayed away from that from the start of this forecast because I knew, based on experience, that typically this scenario is not one to produce a major ice event for the I-95 corridor. If you're looking for an ice event for the I-95 corridor, you actually want the reverse. You want a cold air mass already locked in, and then warm air trying to invade, with a low pressure system trying to cut up towards, let's say, from the Ohio River Valley towards Syracuse. In this scenario, you're racing against time. And the one way to see that race is taking a look at 700 millibar relative humidity. Why, you ask? Well, let's take a look. When you're making this forecast, up to about 4 p.m. on Friday, actually even before that, you can even see in the early morning hours that moisture being driven out faster. And you can see that also in the precipitable water values right here. You reach an apex, right? And there's your heavy rainfall. And then watch that start to disintegrate and leave. So let me pull up the 12Z. It shows up a little bit better. Right when you get your cold air to get into the coastal plain, notice your deepest moisture is now off the coast, and you're getting drier air building in. So again, you're racing time. You're racing the cold air trying to get to the coastal plain and enough moisture hang around to produce ice accumulation. You have a far better chance of doing so up here over the interior. Let's see if we can get... Okay, it's stuck at 30 hours. And I just want to walk through also the surface temperatures finally. There's our warm up. Now let's see, when does it get to freezing? Okay, so we finally get to 31, 32 degrees right around 9, 10 a.m. when most of our precipitation is starting to leave already. Now, when you're forecasting for the coastal plain, again, we're well above freezing here. And then New York City and Philadelphia, we're right around 32, 33. When you're having the subways and whatnot, it's going to stay pretty much liquid. It's really hard to pull off freezing rain in this scenario. The reason why I went enhanced with the ice potential further north and west is because look at these temperatures. They're in the mid to upper 20s. This is definitely going to produce freezing rain. And so you got some heavier bursts, and this can lead to that scenario for an icy threat. So that's kind of how I came about this whole forecast, based on knowing what I know about the climatology of these type of storms and type of scenarios. Combine that with the model guidance that was starting to trend away from a significant ice threat around I-95 corridor, but typically you see that north and west of the I-95 corridor. Combine that with the timing of the moisture transport, then the dry air transport behind the cold front, led to me creating this forecast that's in place. And I'll take questions more on the forecast in just a moment. I just want to touch on the final thing, which is the February forecast. Originally, I was thinking, okay, this is going to be a scenario where we know we have a weakening La Nina. Okay, look, we're already in 3.4. We're already below the La Nina status here for the daily value. Normally, it's -5 and -0.5 and below Celsius, and we're already starting to go above that, more of a cold neutral in 3.4, clearly an east-based La Nina. And you're seeing also the SOI. This is your measurement of the atmospheric influence of La Nina. I like this a lot more than looking at the sea surface temperatures because it tells you more about the impacts of that state on the atmosphere itself. So we already know this. So I was thinking, okay, we should see a collapse in the winter pattern by around the 10th of February, and then we end up mild for the final 2 weeks of February, regardless of what a groundhog or a whatever animal you want to use. That was the idea. The reason why I extended it about another week or so is that I'm seeing on the MJO this signal of getting into phase 3, maybe just touching it before going into phase 4. Phase 3 in the MJO is a cold phase. Now, we know that the MJO is not the driver, but more of a signal. So what caused this signal? Well, we also know that the atmosphere, that the whole pattern this year is driven by what's going on in the polar vortex, specifically stretching of the polar vortex and how that translates to the tropospheric response to that. So what would cause another stretching scenario? Well, I said a couple weeks ago that the way to extend the winter a little bit longer is if we got another shot of warm air, right? Another punch. And so you could see we're already seeing a redevelopment here of the transport from the troposphere to the stratosphere, from the mid-latitudes towards the higher latitudes. We're seeing in the model guidance stronger influence. This is from the European guidance. Again, this is taking your mid-level environment and taking it up into the stratosphere. Okay, you can kind of see a nice chart here of that transport. And then finally, this observation. These are the temperatures at 10 millibars, and notice this warm up here. Okay, again, we start out cold, and then we start getting warm again, and then it starts to push towards the Arctic Circle. Now, it doesn't warm the entire stratosphere. If it had done that, that would have led to a major disruption of the polar vortex and also possibly a split. But we never get to that point, and it's not going to get to that point. All this does is stretch the polar vortex. So, let me go pull up this chart here, and let me show you what that leads to. And on the European, it does the stretch, which gives us an influence into the middle of February now before it reconsolidates. Now, one thing to note here with the polar vortex in the stratosphere, it strengthens. It's still very strong. So this means that we're not dealing with a scenario where the polar vortex is collapsing, but we're still dealing with the stretching of the polar vortex. And we also see that on the GFS ensembles. So what does this tell us? Okay, let me walk through here. I'm going to put myself on there. Okay, so typically when we see this type of scenario setting up in February, you have two factors here. Okay, understanding first of all that the polar vortex and the evolution of that and its coupling with the troposphere is what's been driving our weather pattern, not the tropical forcing. You can put aside La Nina. You could put aside the MJO as more of a signal rather than a driver. And then you can take a look and see what's happening with the polar vortex, how it's influencing the troposphere, i.e. 500 millibars. And what this tells me is that, one, if you're looking for high latitude blocking like a negative NAO, forget about it, okay? You might see a blip here or there, but nothing sustained. So that means that your storm impacts for rest of February is going to be very much hit and miss. It's going to be another scenario where everything has to line up just right. And it's also going to lead to more wintry mix type scenarios than pure snow scenarios. I'm not saying that it can't happen as a pure snowstorm over the next 18 days, but more often than not, it's going to be more of these snow to sleet to freezing rain to rain, or rain over to snow type scenarios. With that said, because the polar vortex is strong, this leads to a scenario where the polar jet stream is more likely to be contracted. In other words, your polar and Arctic air masses are going to have less staying power in February. So you end up with a shot coming in, let's say falls down to the 20s and 30s, but instead of lingering for 5 days, it only lingers for 2 or 3 days. And so you get a rapid moderation. That typically means that your winter storm potential has to be set up just right at the right time. I also think that once the influence of that warming that we just saw subsides, that we're going to see a lifting of the polar jet stream, more of a zonal pattern. And I think that's going to be around February 20th. And that's going to lead to just a mild Pacific air mass dominating much of the United States. But between now and February 18th, I think that's your potential there for snow, sleet, freezing rain, an icy mess potential, and waves of cold air still being a threat. So that is kind of like my thought on February. I think that March is going to start off warm. We'll have to watch out to see the interaction between the polar vortex and the troposphere as the polar vortex starts to naturally break down as it does in the spring. Sometimes what happens is that when the polar vortex begins to break down naturally, that we get a rogue cold shot that comes in. But I still need more data to kind of work on that to see how that plays out. Sometimes that hits North America. Sometimes that hits more of like Asia. So we'll have to watch to see how that plays out. So those are my overall thoughts. I'm going to basically now answer all your questions because we are loaded. Let's see here. I'm just going to check up on you. Wow, yep. Everything's busy up here. So let's get to answering the questions. Let me scroll up here and I will start. Okay, so card axes. The meso models are really pumping up the ice amounts. Convective feedback, the cause. Here's the thing with the ice maps. And, this is a good chance to talk about how to forecast winter precipitation with these models. Let me make sure. Good. Okay. Google Chrome. Good. Okay. So typically what people want to do when they forecast for winter precipitation is that they just want to pull up an ice map or a snow map, take this, and post this on social media. Now, in this ice map, you got 0.7, 0.9. This would be catastrophic icing. Okay, this would be a type of scenario where you lose power and you would be shut down for a good week. The problem with this is that what this is really doing is taking the QPF, which is the amount of moisture put out, and then saying cold temperatures, and therefore everything that falls as rain will freeze. That's what this is doing. That's not reality. That's not how freezing rain works, especially with the temperatures that we're going to be dealing with and the scenario that we're going to be dealing with. I'll take another example of a snow map. Okay, now we all know about snow ratios, right? And we had a really good lesson about that last weekend, right? Where the snow maps that are being put out there don't actually match reality half the time. So you have this snow map here, and you don't have any consideration because it's 10 to 1, whether your ratios are 8 to 1, how much of this is mixing with sleet, and how fast is the atmosphere cool to change the snow ratios here. So then you might try another one called a Kukkersian map, which is basically trying to adjust for those ratios. But even that, you can run into some errors because it's not as fine-tuned. This is how you deal with forecasting for wintry precipitation. First and foremost, and again, this is going to take longer, it's more tedious, but it's more accurate. You don't worry about the snow map or the ice map, because anyone can read that. You take a look at the QPF that's being put out. Okay, now this is liquid precipitation. So obviously if it's rain, it's a heck of a lot more accurate because rain is rain. Okay, rain is, there it is, done, right? And if you're not sure about the QPF coming out, you can use the precipitable water values I was showing to see, okay, how much moisture is in the atmosphere. So let's say typically above 1 inch, that would support a very heavy rainfall event. And when you start getting to 1.5, that is some torrential downpours. So we know we can get to 1 to 1.5, so it would easily support these 2-inch rainfall events. Now, how much of this is actually ice? Well, the model guidance would say half of this is ice. But we just saw the temperatures and the dry air transport cut everything down really quickly. Combine that with the fact that, okay, you have temperatures falling, but that doesn't mean your boundary layer, your actual surface is freezing. So again, we'll use a little prop here. We have our surface, right? Your air temperature is right around freezing, but your surface here is still slightly above freezing. And again, when it comes to freezing rain, the difference between 32 and 33 degrees is huge. So this right here, you have your rain coming down. It's starting to cool off, but this has been sitting in 40 and 50 degree weather. So it takes longer to cool down. So the amount of ice that actually accumulates on this is nowhere near 0.7. Okay, it's more like 0.25. Okay, so decimal 0.25. All right. So as a result, if you try to put out an ice map that is 0.7, it's going to lead to a lot of error. So is it convective feedback? No, it's a poor demonstration of how to use a QPF map and then try to convert it into something graphically easy. You can do it with snow most of the time, but it's really dangerous to do it with ice because it doesn't factor in a whole bunch of factors that you don't think about when, I don't want to be elitist or anything, but look, when you're in a meteorological class and you're dealing with dynamics and mesoscale forecasting, these are the little details that make a difference in the forecast. And this is why I always get annoyed when people post ice and snow maps, because it's far too generic and doesn't take into account of a lot of different factors that simply you cannot do or demonstrate with model guidance. This again is why I am so much against automation, because it doesn't take these little factors that really human touch needs. So in terms of the ice amounts, no, it's not convective feedback error. It's just limitations of what you could show in model guidance. And that sometimes you just need to look at the data, know from experience, and say, no, an inch of ice is not going to be developing out of this storm because of the nature of the storm that we have. Let's see here. Okay, Jonathan Cohen asks this question for tonight. It looks like Philadelphia, Wilmington, and Baltimore are only cities in the Northeast without a snowfall of 10 plus inches in the past 6 years. Is it due just to an unusually long run of unfavorable storm tracks since the blizzard of 2016, or is there another explanation? Well, there's a couple of factors. One, there is the mesoscale banding factor, which has been very interesting to monitor. We actually had a huge debate after our winter storm that we just had with Dr. Cohen and a couple, you might have seen it on Twitter, where there was a debate as to whether or not winter storms themselves are more intense. And I argued that no, they're not more intense, but there's more mesoscale banding. Why is that important? Well, look at the observation you just pointed out with Philadelphia, Wilmington, and Baltimore. What do they all have in common? They're all separated away just enough from the coastal plain, the immediate coastal plain. So what you have ending up here, and this is a perfect map to use, is you have all this warm water out here. You have an Arctic air mass coming in. And where are we constantly seeing our strong mesoscale banding? Well, along the coast. Why? Because we have a strong thermal gradient. So what's happening here is that the storms themselves are developing like they always have, but because of the strong mesoscale banding, you're getting all your focus of heavy snowfall on Long Island, Connecticut, New York City sometimes, the Jersey Shore. I mean, look at Atlantic City. Give me a break. It's been insane down there, right? Well, those factors leads to a lot of lifting, a lot of rising air, which translates to a lot of sinking air over Philadelphia, over Baltimore, Washington. So that's limiting your potential snowfall. So when you just look at the pure statistics and not dive into individual storms, you miss this very, very important factor, that the factors of the urban heated island effect, the factors of the warmer waters just off the coastal plain, the robust Gulf Stream that we're dealing with, combined with these Arctic air masses, all leads to more convective precipitation. So that's why you're seeing what you're seeing in the snowfall totals. Now, can this change? Absolutely. I would not be surprised if we see a shift back based on the evolution of the storms. I think that one of the factors that you'll see change, if we get a weak El Nino next winter, which is possible, I'm not 100% confident of it, but let's just say that happens, then you got a better potential for more Miller A storms. And that's like similar to the storm we just had, where you have a higher threat for more widespread 10-inch snowfall, but your heaviest snowfall will be along the coast, but you'll still have a potential for, let's say, 12 inches in Philadelphia, while the coastal plain gets 16 because of that mesoscale banding. So, but I think that's the signal that you're seeing. Card says, saw that there's a CME that hit yesterday. Yep, but was so weak it didn't even set off a geomagnetic storm. Yeah, the sun's been weak, very weak. It's active, but weak. And the reason why, for some of you who may not be familiar, every Friday in the premium section, I do a analysis of what's going on with the sun for more of a climate slash long range forecasting influence, because the sun does matter, and there is some indication of a grand solar minimum possibly developing in the next decade. So I'm kind of keeping an eye on that data. And one of the things we're noticing is that even though we're moving into an active period of the sun, that the solar winds and the solar particles associated with this active period is one of the weakest that we've seen in about 100 years. So it's been very interesting to see it evolve. We're kind of moving into a very unique and very unprecedented environment and setup here for monitoring the sun, is that now we have all this technology to really test a lot of theories about solar evolution, how that impacts the surface of the Earth, how it impacts the ionosphere, the stratosphere, all these factors that we think we know, but we're not sure about. And that includes the QBO and whatnot. This is why when it comes to climate change, when people say, well, the sun isn't important dealing with climate change, I disagree, because of the fact that we have our climate models based on assumptions of how the sun impacts the Earth and how that interacts with greenhouse gases. And we're already starting to see that some of those assumptions were wrong, or perhaps we need to adjust for them. That doesn't mean, again, that we could just pump CO2. What I'm simply saying is that some of the assumptions in the climate models may not be as accurate as we think in terms of solar influences, because now we're actually in real time with such improved technology are actually putting those theories to a test, and we're learning more and more about the sun and how it impacts the Earth. And I think it's exciting. I don't know why it's controversial to even say something like that, but I think it's really interesting, and I think it's going to allow us to improve our forecasting so that we can better prepare for future climate changes and evolutions of the climate. So it's very interesting stuff, and I'm personally keeping an eye on it. And every Friday we go over the latest data of what's going on with the sun. Part of the Pocono is just west of Mount Pocono, in the middle of the salsa dish. Top of Mount Pocono is notorious for freezing fog. Yes, it is. It's a perfect scenario set up over there. Even 5/100ths of an inch of ice and a coating of snow on top can be really dangerous. Yes, indeed. Ice is always, I hate forecasting for ice, because it's never a scenario where, oh, it's only a dusting. It's only a trace. Even a trace can cause a really bad accident, okay? So, especially when you have your temperatures just falling well below freezing after the event, you can't get rid of it. You can't like shovel it out of the way. You can't run around a road with a chisel. You know what I mean? So, I hate forecasting for ice. I'd rather either just have snow or rain. Do you expect more ice threats in the next couple of weeks? Yes. Yes, I do. I would be, in this type of scenario, not so much, but I would be far more concerned about we getting an Arctic air mass coming in, and then it starts to retreat, and we get that snow over the ice, then finally rain. Those type of scenarios I'm very much concerned about, and we'll be keeping a close eye on. What is the timing of changeover on Friday? Well, that's a perfect question. It's a good time to, let's see if we can pull up the new HRR. Okay, so we'll walk this through. Not far enough out yet. Let's use the NAM then. And I'm using the NAM. Again, notice I'm using the NAM more than the European guidance. You might be wondering why. And the reason why is because you use the right tool for the right problem. The European guidance is a synoptic model, which means large scale. The NAM is more of a mesoscale model, which means small scale. The timing of the changeover of precipitation is a boundary layer, small scale, mesoscale question. So you use that tool, the NAM, to answer that question, which is more likely to be more accurate. So you use the HRR and the NAM model guidance. You can use the high-res European guidance, but I like to double check it with the mesoscale models that I know are usually successful in this scenario. So through tomorrow, we're going to be dealing with showers up through midnight. As we get past midnight, you're going to start to see more frozen precipitation over the northern interior, and then that slowly slips down through the morning hours. By around 8 a.m. or so, you start to get ice north and west of the major cities. And in fact, the 0Z is not out yet, but we'll get there. And then as the precipitation is coming to an end, late in the morning, more locations start to change over to freezing rain. But notice your heaviest precipitation is now off the coast. So this is more of a light to moderate precipitation rather than widespread heavy precipitation. And as we get towards the early afternoon, all snow to the north and west of the cities, a wintry mix of sleet and freezing rain along the coast. And then our final burst of some light snow in the evening hours towards around midnight. Again, could get you a dusting to maybe an inch. By this point, you have your temperatures in the 20s falling into the teens, and so there won't be any hindrance of snow accumulation. Let's see here. The Weather Channel named an Arctic cold front. Really? They named this? Oh, well, doesn't surprise me. They're going to be naming thunderstorms next. Do you see any flooding threat? Yes, especially urban flooding, because you have the snow melt, you have debris within the snow, it gets clogged in the drains. So there you have it. Has it been cold enough for the warm air ahead of the front to cause flooding from ice jams? Not so much. I don't expect that to be a concern. The race in time almost always is the cold air moving slower and too late to change over fast enough, and you just end up with plain rain here in Allentown. Yeah, that's from Snow Boss, and I completely agree. This is why I'm nowhere near as aggressive as the model guidance in terms of the ice or the snow. I was less than the snowfall in all the model guidance, and I reduced it even more this afternoon before posting the public one, just to get a good timing. Rob Allen asks, I am late, so don't worry about it. Are you buying 18Z GFS compared to the 12Z suite that the cold air is able to push in faster? No. The GFS is notorious for cold bias, and what I scrap the GFS in this scenario. And quite frankly, the regular European I'd scrap, and I'd go with the mesoscale guidance because it does a better job of handling those colder, the low-level dynamics of the cold air pushing south. I think the GFS is, well, the GFS. I would take in the GFS or the European guidance more so if it matched the NAM and the HRR. And the models that match the NAM and the HRR guidance that I'm seeing right now is associated with the European guidance. It matches it up much better. So that's why I would go with that combination. So what I'm doing here is I'm looking at the mesoscale guidance here. And I'm saying, okay, this is at 0Z. This is 0Z guidance HRR. It's at the 33 hours. This is 4 a.m. How well does this match up to the European versus the GFS? And the European matches up with this a lot better than the GFS. And the reason why that's important is because, as you can see with the HRR, it does a better job with analyzing the low-level boundary layers. And that's how you get these kind of like these kinks and this evolution in the precipitation shield, because it handles that movement of the cold air transport a lot better. And the guidance that basically supports that better is the European rather than the GFS, which just looks way too fast and way too aggressive. Okay, George Gurian. I hope I'm pronouncing the last names correctly. God knows, I mean, I'm excellent at butchering the English language, so apologies ahead of time. Thank you for all you do. No problem. Thank you for joining. It seems the 18Z guidance, specifically the GFS and NAM, but even the Euro, are predicting greater than quarter inch of freezing rain. Yep, we already talked about this. Are you concerned that your quarter to half inch of ice will need to be expanded south? No. Again, this is, again, and it's not your fault, because you're looking at these maps and you're saying, holy smokes, look at all this ice. 99% of the time, this scenario is overdone in the model guidance. And here's the thing that you want to compare. When you have cold air racing in, remember, it's cold, dry air. So you're cutting down in the back of the precipitation shield, and you're reducing the intensity while the cold air is coming in. If you're looking for a scenario where you're going to have significant icing, what you want is a cold, dry air already in place, and then the moisture invading. And then what you're looking for is the speed in which that cold air gives way. In that scenario, that's when I'm more aggressive with the ice potential, because it's not a case of the cold air chasing the moisture in. It's more of a case of the moisture trying to route the cold air out, which takes a lot longer, which then you can make a case and make more sense physically for the greater ice totals. When you have an Arctic air mass coming in, remember, it's cold, dry air. So the back of your precipitation shields are already being eaten out. Okay, it's being cut down quickly because of the drier air coming in. And we can see that very nicely in the precipitable water values. In fact, let me see if I have precipitable water values on the HRR. I think I do. Here it is. This is out to 35 hours now. Now here we are tomorrow, and notice our values are increasing ahead of the cold front. That's your warm air and moisture air transport, right? Now here comes your Arctic air coming in. Now watch the back end of this. Watch back here. You see this gradient? So you have your cold air come in, and you see this gradient? This means that you have dry air coming in, and this means that the intensity of your precipitation is all out ahead of the cold air transport. As the cold air is bleeding in, your heaviest precipitation is leaving, and the model guidance has a hard time with handling not only the cooling of the atmosphere, but the cooling of the boundary layer itself. So it basically says, okay, all this rain is falling, it's going to be ice. That's what it's saying, when in reality, that isn't what happens. Are these kind of powered changes something that the models have difficulty earlier on, resulting in storms that come and go quickly on runs because the models are not able to grasp the chaos? Yes. Short answer, yes. There's so much going on in the atmosphere that there are so many factors, from the short wave, different short waves, the orientation of short waves, the speed of the short waves, that you get a lot of phantom storms, and you get a lot of scenarios where basically you get a lot of situations where there are storms that have formed on the model guidance that doesn't make much sense. Okay? At the same time, you can get a storm pop up in the guidance with only 4 or 5 day lead time, because the short waves tend to interact just right. So your job is to pick out what are those potentials and how well does that match up on a water vapor satellite picture. Significant ice is somewhat of a rarity in New Jersey, yes. Um, how much ice do you need before you get a significant damage? I'd say anything over a tenth is trouble. Um, not only for power outages, but remember, you can get a power outage by someone unfortunately getting into a car accident. So anything over a tenth is going to be a significant problem. And again, this area up here of basically a quarter to a half an inch, well, that's going to open up the scenario like around Scranton, extreme northwest New Jersey, where you're going to have some ice concerns. I would be on the lookout for power outages. So usually leads to some significant problems. Let's see, is a tendency towards banding of mid-Atlantic Northeast winter storms related to negative AMO? That's a good question. You know, the problem with making that determination is the last time we had a negative AMO, we didn't have the radar capability or observational capabilities that we do now. So it's hard for me to make a definitive answer on that. It certainly could be a factor if you understand that a negative AMO typically leads to above normal sea surface temperatures on the East Coast, around the Western Atlantic, and near to below normal sea surface temperatures around the tropical Atlantic, then that would make sense. But at the same time, we were in a negative AMO environment when we started to see mesoscale banding as well. So those two factors, it's hard to make a definitive answer on that. Is it more mesoscale banding, or are we just better at seeing it with technology? A little bit of column A, a little bit of column B. We definitely have a better ability of seeing it. On the other hand, the snow rates that we are seeing, in some cases, are not really have never been recorded like we are seeing now. We're pretty good at picking up snow rates in the 80s and 90s, and we were nowhere near what we're seeing right now on a consistent basis of 1 to 3 inches per hour type snow bands. I'm seeing that more and more in our winter storms than what I was seeing even when I was starting out as a meteorologist in the early 2000s, where we'd get a band or we'd get a mesoscale band or a deformation band, and that would really enhance your snowfall. Now I'm seeing this more frequently, and something that I have to incorporate in my forecasting more and more. So I think that the factors in change is not the strength of the low pressure system or intensity of the storm wholesale, but these mesoscale boundaries that are becoming more enhanced. When will the AMO flip to cold phase? Probably about 25, 30 years. And how would that impact East Coast winters? Well, the theory is that a negative AMO typically is more supportive for a negative NAO, and a positive AMO is more supportive for a positive NAO, but that isn't locked in. I think a NAO state is more driven by the stratospheric influences and the evolution of high latitude blocking potential than what's going on in the Atlantic in terms of sea surface temperatures. But I think a negative AMO enhances that potential and produces more of a staying power. So right now we're in a positive AMO environment. Just a heads up, 0Z NAM heights are significantly lower so far compared to 18Z. Yeah, but that doesn't really mean much to me in terms of the structure of this forecast. It would make much more of a difference for me in terms of forecasting if I was doing Buffalo or Cleveland or something of that nature in terms of snowfall potential. What happened with the potential Sunday, Monday coastal storm? Is it still possible? I'm less confident of it. I'm not really seeing much support in it in the ensemble guidance. And it's because the two short waves so far are not in sync. I'm keeping an eye on it. Thus, the reason why I kept scattered snow showers in the forecast. But if I don't see any improvement in the ensemble guidance for that threat by tomorrow morning, I'm pretty much going to remove it from the forecast So we'll see how that plays out. I remember one big ice storm in the mid-late 1970s growing up in central New Jersey. I remember this one. I wasn't alive, but I remember doing a research on it. Had about 4 or 5 inches of snow and very good layer of ice. Yep. When was the last major ice storm in our region? Um, I want to think back to 2003. I think we had like a really widespread. We actually had one like 2 years ago that was producing significant ice in around Trenton, the I-95 corridor. That was pretty good. All right, let me check out YouTube and see what we got here. Holy smokes, boy, we are busy tonight once again. Well, it's duck season. Let's see here. General question: how does the I-95 corridor look for travel on Friday? Look, if you got to travel on Friday, take some extra time, drive slowly. Roads are going to get, as you get, the morning will be fine. Because the morning you're going to be in the 40s and 50s. I mean the early morning. Let's say like the morning rush hour. The evening rush hour is going to be a mess with not only precipitation changing over to freezing rain, sleet, and snow, but also after that precipitation's over, your temperatures are going to be falling through the 20s and teens. So anything that's left in the ground is going to be freezing. So I would use extreme caution as you go on through Friday. In the late morning and afternoon hours, it's not going to be pretty. Let's see here. Sun lives matter. That's wonderful. Let's see here. Steve, thanks for the analysis. What time for? How do you believe in global warming debate, climate, and weather? How do I believe? I take the science. I don't believe. All right, my approach to global warming is simple as this. I do not believe in extremes in terms of approaching any solution. Extreme solutions never work because you have to deal with the real world. It's easy to make extreme solutions like everyone should live in a hut or we should all burn coal when you're not dealing with real people and real life scenarios. But I will say this is how I handle it. I just go with the data. I go with the observations and go piece by piece. Okay, you're never going to hear me say extreme solutions one way or the other. I believe in technology. I'll put it that way. Let's see here. Okay, so let's see. Go back to the premium chat here and holy smokes, it's 9 o'clock already. I didn't even realize it. When was we had the one recent winter with ice notwithstanding, southeast and south winds. Yeah, that's the other thing too. Heavy rain and clogged drains equals hydroplaning. Yep, that's a factor as well. Let me see. Pull in. I'm going to pull and try to see if I can pull in some more 0Z guidance. And then we're going to shut it down for the night. But specifically, I want to see the HRR guidance. Well, there's our precipitable water. Now, watch. See that rapid cut down? See this gradient? This tells you that when the cold air comes in, the heavy precipitation is getting driven out quickly. And this is at 10 a.m. on Friday. And you see that scenario setting up. So that's a big warning sign against heavy ice. Take a look at the simulated radar. And yeah, you see this right here? See how that matches the precipitable water values? Look where you have your heaviest rainfall, your heaviest precipitation, and then your frozen precipitation chasing it behind it. So this would argue against an enhanced ice total, that like what you're seeing in the model guidance. So by the time that the cold air gets down to the coastal plain, Look what the HRR is doing. And this is a mesoscale model. This type of model is designed to handle these type of questions in terms of low-level cold air transport. And you see what happens? By the time the cold air is getting in, the bulk of your precipitation is leaving. See, now that's a very important observation in the model guidance. And we match that up with what's going on in the amount of moisture in the atmosphere, the timing of the cold air transport. And we could break this down even further. Okay, here's your 850 millibar temperatures. Notice how long it takes for the cold air transport to get down, because the winds are running parallel to this cold air, right? But then when we go down to the surface, 2-meter temperatures, it's a little bit more aggressive. It's a little bit faster. But the cold air is chasing the moisture. And so notice in this scenario, again, your temperatures around the I-95 corridor, 35, 38, 40, 43. Your coldest air, again, this is where I have the most significant ice, is where you have your temperatures falling into the 20s. It makes sense, because in these areas, the cold air is able to bleed in faster, because it's closer to the source of the cold air, where you have temperatures in the teens up here in central and western New York, able to push into the Poconos and the Catskills a lot easier than down towards the coastal plain. So where would you put your most significant icing? Where you're closest to the cold air at the lower levels, not down towards the I-95 corridor, because the core of that cold air is much farther away and has to go through a lot more obstacles, like the Appalachian Mountains, to get there. Oh, and by the way, you start off at 4 a.m. in the morning around 50 degrees. So that also means that your boundary layer is much warmer at the start, rather than in the Poconos, where you're starting off at 34 degrees. See, less cooling is needed, less energy is needed to get you to that point of producing icing. And so go back to simulated radar, out to 45 hours, and you can see the precipitation. By the time the precipitation is leaving, the cold air is finally invading. On the NAM model guidance, let's see if it's trying to play up that same scenario. Only out to 18 hours. So this is still in the middle of Thursday, so it's going to take a little bit longer to come out. But I'm willing to bet it's going to be the same scenario. So just to go over again, finally, this is the theme of the forecast. Along the coast, right around rush hour in the afternoon hours, be mindful of a trace to 1/10 of an inch of ice, a trace to 1 inch of snow. And then north and west of the I-95 corridor, that's where we're dealing with more significant ice. Anyone north and west of the I-95 corridor, north and west of the major cities, I would use some extreme caution if you're going to be traveling, and just be careful. If you have to drive, if you have to travel, I'm pleading for you to either go tomorrow when you're not dealing with this ice, you're well above normal temperatures, well above freezing temperatures, you're just dealing with rain, or wait till Saturday. You do not want to be driving in snow and freezing rain. If you have to drive, take some extra time and drive slowly, like below the speed limit by 5 to 10 miles per hour. And even more so as you head up towards Scranton. I think this is where you're going to get a big ice hit here, because this area that I've highlighted is an area where you have temperatures falling into the 20s and still enough moisture hanging around where a lot of that freezing rain is actually going to accumulate. So that's where we stand for tonight. I want to thank everyone for coming into the chat. I really, really appreciate it. Everyone on YouTube, again, thank you for joining, and I really appreciate it. Again, over 2,000 subscribers to the YouTube channel. That is amazing. And I just want to thank you all for that opportunity of providing you weather information. Again, thank you, everyone. Have a wonderful night. And as always, stay safe out there.